Hi guys, welcome to the Section 9 review. So question number 1 says, given the following exponential equations, state whether they are growth or decay and increasing or decreasing. Okay, so if we look at the b value, okay, that's what we need to focus on to determine if it's growth or decay. If the b value is a number that is bigger than 1, then that is growth. But if the b value is a number that's less than 1, remember not necessarily if it's negative, but that it's less than 1 as a positive, because the negative would mean that it's a reflection, then that is decay. So in this case, 1/2 is a number less than 1, so this is decay. On part B, our b value is actually has not been simplified yet. It's 1 minus 0.1. So if we simplified it, that would be -7 and then 0.9 to the power of x, which means that the b value is 0.9, which is again a number less than 1. So this is also an example of decay. On part C, the 2 is the b value. That's what has the power of x. So 2 is a number bigger than 1, so that is growth. On part D, this has not been simplified for the b value, so we would go ahead and simplify it. It would be 1.06, so that number is a value bigger than 1, so that is growth. And then the last one we have here, that it is 2, but if we simplify, because notice the power is -2x. So if we actually simplify this, this would be, as just power x, would be 1 over 2 to the power of 2 with just the regular power x. Okay, in order to determine growth or decay, you really want to simplify that number. So 2 to the power of -2 will be 1 over 2 to the power of 2, which means that the b value is actually 1/4. And so then this is actually decay. In the question, they also wanted me to state whether it was increasing or decreasing, and that's easy to determine because you really want to make a rough sketch, okay? Now, don't just go ahead and say growth is always increasing and decay is always decreasing, because remember, if you are reflecting, then that is going to change it. So on part A, though, it is not reflected at all, so this would visually look like a decay graph. So it will look like this, and so this is decreasing. I'm going to use DEC for short. So part A is completely done. Part B, notice that this negative out in front is multiplying y by a negative, which means that this is an x-axis reflection. So even though my original graph is a decay, just like the one we just did on part A, it is reflected over the x-axis, which means that this is actually what the graph looks like. So this is actually increasing. So you want to be careful. You want to consider the transformations that are happening to the growth or decay function. This one is a growth function, and notice that there is no reflection. So this would just be the function would stay as a growth function. So this is increasing. For part D, this is a growth function, right, which normally looks like this. But again, with that negative out in front, that's an x-axis reflection. So that means that it's going to be reflected here across the x-axis. So this is actually going to be decreasing, since it is actually going down as we follow the graph from left to right. And then last one, we have a 3 to the power of 1/4. There's no reflection here over x-axis reflection. So this is a decay function, which looks like this. You could have, so it is decreasing. You could have also at the beginning, right, if we're thinking about 2, but then reflecting that over the y-axis would flip it over. Okay, so that one, it will be decreasing. All right, number 2. A virus spreads through a network of computers such that each minute, 25% more computers are infected. Assume that the virus only started on one computer. Now, you want to be careful here because they're saying in the question that it is infected, which might make you think that it is decreasing. But it's not that the infection, nothing is actually going down. The infection is going up. More and more computers as time goes on are getting infected. So this is actually a growth problem. Okay, the rate that it's being infected is 25%, which would be 0.25 as a decimal. So the exponential model, since this is a growth, my growth factor will be 1 plus the rate. If it was decay, it would be 1 minus the rate. But again, here, the amount of computers that are infected is going up. So my function here, as a function with respect to time, would be how many I started with. I started with just one computer being infected. And then my growth factor will be 1 plus the 0.25. And then that's going to be to the power of t, how much ever time has passed, or intervals of time. So if I simplify this would be f of t equals, and then 1 times anything, you could just leave it off, and then it will be 1.25 to the power of t. And you could put that 1 in front, or you could, leave it out with the 1 out in front. You could put 1 there, or you can, leave the 1 off because obviously it's the same number. Okay, what is the number of infected computers after 40 minutes? Remember, t here is going by every single minute. So we have 25% of more computers being infected every minute. So t here is per minute. So when we're saying how many are infected after 40 minutes, that means that t would be 40 since 40 minutes have passed. So here I'm finding what f of 40 equals, which would be just finding what 1.25 to the power of 40 is. So I would use my calculator, and I put 1.25, and I raise that to the power of 40, and we get 7,523. Now this is computers, so I will use whole computers. I'm not going to use decimal, right, because there's not like 0.16 of a computer. So it's roughly about 7,523 computers are infected after 40 minutes. Wow, that's a lot of computers. All right, number 3, a cup of green tea contains 35 milligrams of caffeine. The average teenager can eliminate approximately 12.5% of caffeine from their system per hour. Okay, so we are getting rid of the caffeine, right? So this is a decay question. Now decay, the decay factor is going to be 1 minus the rate. So the rate as a decimal would be 0.125, all right? And we started with 35 milligrams of caffeine, so that's our starting initial value. So the exponential function here would be the function that represents the amount of caffeine over time t per hour. T in this case would be the amount of caffeine per hour. That's the rate. So it would be 35 that we started with, and then times 1 minus the rate, 0.125, and then to the power of t, how many hours has passed. So if I simplify this, it will be 35, and then 1 minus 0.125 is 0.875. And of course, the power t stays. So that is the function that represents the amount of caffeine over time t, how many hours have passed. Now, B, it says, estimate the amount of caffeine in the body after 3 hours after, drinking the tea. So since t is per hour, that means that we're going to plug in t here as 3. So figuring out how much caffeine is left is just by figuring out what 35 times 0.875 to the power of 3 is. So again, I could take out my calculator, and then I would do 35 times the 0.875 to the power of 3. So that's 23.44, etc. So since this is the amount of caffeine, and they started with a whole number for amount of milligrams is already pretty small measurement. So I could keep it as a whole number and do about 23 milligrams is fine. All right, number 4, given y equals 0.2 times 3 to the power of x, identify the following. So we need to figure out what the initial value is. That is always this first value right here. So that's 0.2. The growth factor would be the b value, which is 3. And then the rate, remember that the factor is figured out by adding 1 plus the rate. So if the factor is 3, that means that 3 equals 1 plus the rate, which then if I subtract 1, that means that the rate is 2. So that would be the rate as a decimal. They want the rate here as a percentage. So if we move the decimal point twice to the right, it would be 200%. Okay. Number 5. So we have given an exponential function with 45% decay and a y-intercept of 5, identify the following. So the y-intercept is the initial amount, is the initial value. So that would be 5. And then the decay factor is determined by doing 1 minus the rate. They did give us the rate actually in the question right here. So the decay rate is 45%. And we would figure out that decay factor by doing 1 minus that rate as a decimal, which would be 0.45. So the decay factor will be 0.55. Right. On number 6, we are given a table. They want us to determine the growth or decay factor and the growth or decay rate and the initial value. Okay, in this case, notice that the values are going up as x increases. So this is definitely growth, not decay. To figure out the factor, we just figure out how much we actually multiply by to get from one number to the next. So if you use your calculator and you check, it's 6144 multiplied by 4 gives us 24,576. You could also figure out this number by using division. So if we do 24,576 divided by 61,044, we get the 4. So the actual factor, what we multiply by to get one number to the next, is 4, which means that the rate would be 1 plus r equals that factor of 4. So the rate is 3. You could write it as a decimal, or you could write it as a percentage, which would be 300%. Lastly, the initial value, which is the a value. Remember, your formula is y equals a times b to the power of x. And so in this case, we can use any point here, any xy point. I could just use the first one, for example. So my y value is 6144. A value, my initial value is what I'm trying to find. B is the growth factor, which is 4. And then to the power of x, which is 5 from this xy point that I selected right here. So 4 to the power of 5, I could put that in my calculator, which is 1,024. So this is going to be a multiplied by the 1,024. And so I could get a by itself, by dividing by 1024. And if you do 6144 divided by 1024 on your calculator, you get that the A initial value is 6. All right, for number 7 and all the way through 12, actually, they want us to match the function with the correct graph. So we have some options here at the bottom, and we need to match them. So the best thing to do is try to think about the general shape of the graph and try to match it that way. So on this one, since the B factor is less than 1, this would be a decay. And also notice that the transformation is that it's going to be shifted down 2 units. So if you're shifting the graph down 2 units, that means that also the horizontal asymptote, which is normally at the x-axis y equals 0, it's going to be shifted down 2 units as well. So that means that this horizontal asymptote is going to be on y equals -2 rather than the x-axis y equals 0. So if I look at all of the options here, the only one that looks like decay is B and D. But notice that D has the horizontal asymptote still at the x-axis, y equals 0, and B does have that horizontal asymptote at x equals -2. So number 7 is the B graph. Next, number 8. Notice that we have 2, which normally would look like growth. However, with this negative on the outside, we are reflecting over the x-axis because we're changing the sign of the y value. So we start with a growth graph, right? However, it is reflected over the x-axis, so it will look like this. And it's also being shifted up 1 unit, so the horizontal asymptote is not going to be on the x-axis, is going to be up 1 unit. So this horizontal asymptote will actually be at y equals 1 since we are shifting it up 1 unit. So if we look at all of the options, the only one that matches that general shape would be A. Notice that it is has that shape flipped over the x-axis, and the horizontal asymptote is at y equals 1. So the number 8 is A. Okay, next up, number 9. So on number 9, we are, this is a growth, and there is no reflection, so it will stay as a growth graph. However, it is shifted to the right 3 units and up 1 unit. So it is going to look a little bit more to the right and up 1 unit, which means that the horizontal asymptote will be at y equals 1. So looking for a growth function that has the horizontal asymptote at y equals 1, and it looks like it's shifted to the right a little bit, would be f. So number 9 is F. Okay, next one, number 10. So this is a decay, and there is no shift at all. There is a vertical stretch, which will just make it look a little bit more flat. But overall, the general shape is going to be decay, and we haven't shifted up or down at all. So our horizontal asymptote is going to stay right on the x-axis. So we're just looking at a decay graph that has the horizontal asymptote at the x-axis, which would be D. Okay, next up, number 11. So number 11 is a growth, and it's shifted to the right 2 units. So, but it is not shifted up or down at all, so that horizontal asymptote is going to stay right on the x-axis. It's just going to be shifted right a little bit, but it is a growth graph. So that would be E, which has the horizontal asymptote right on the x-axis, and you do see that the graph looks shifted to the right a little bit. Okay, and then lastly, number 12. So on number 12, this is a growth graph because the b value is 2, but it is shifted down 2 units. So my horizontal asymptote is going to be at y equals -2. So it's going to be shifted down 2 units from the x-axis, which means that that graph is C. As you see, the horizontal asymptote at y equals -2, and it is a growth graph. Okay. Next up, number 13, write the equations for each exponential function below in the form y equals a times b to the power of x. All right, so there's multiple ways to go about this. I would say definitely what we always need first is our a value. Remember, that is the initial value or the y-intercept of the graph, which is when x equals 0. For all exponential functions, that's what we're looking at here. So on part A, my y-intercept is 4, so this will be our a value. Our a value is 4. And then our growth factor, there's multiple ways to find the growth factor. I would say the easiest one is you can go ahead and make a table of values. So we have the 0, 4, which will be our a value. And then we have the next x value is 1, which the y value is 8. And then the next x value is 2, which the y value is 16. And we can just look at what happens as x goes up by 1. All of these y values are being multiplied by 2 each time. So whatever you multiply by, that is your factor. So in this case, this would be my equation, y equals, a value would be 4, and then times the growth factor, I multiply by 2 each time, and to the power of x. Right, on part B, I can do a similar thing where I look at the y-intercept, which is 24. So my a value is 24. And then I can make a table of values. So 0, 24, that's my a value. And then at 1, we have 12. And then at 2, we have 6. So you could see here that each time I'm multiplying by a half. 24 times a half is 12, 12 times a half is 16, and so on. So that means that my decay factor in this case is 1/2. So the equation would be y equals 24 times 1/2 to the power of x. The other method to go about this question, if you can't really tell what the growth or decay factor is automatically from looking at the values, you could pick any xy point. So then plug it into the equation. So 12 equals a value 24. And then in this case, we're pretending like we don't know the growth factor. So we're trying to find our growth or decay factor, whatever it is. So we're trying to find b. And then to the power of the x value being 1. And then you solve for it. So like 12 equals 24 times b to the power, well, b to the power 1 is just b. So 24 times b, and then divide by 24. So we would get 12 over 24, which if we simplify is 1/2. So that's a way to find the b, the growth or decay factor, if you can't really tell based on the numbers by making a table of values. So this is like method 2 to find the growth or decay factor. If method 1, making a table of values and just kind of thinking about what number do you multiply to get to the next number works. All right, next up, number 14. So on number 14, we're asked to find all of the key features, and we are also asked to graph, and they're asking us to use interval notation. Okay, so looking at the graph, okay, We start with negative 4 times 2 to the power of negative 2x minus 1 plus 2. Right? There's a lot of transformations here. They're not asking us for the transformations. They're just asking for a table of values. So what I can do is I can just use my calculator and plug it in. Okay. So we have negative 4 times 2, and then that's to the power of negative 2 times whatever x is. X right now is going to be negative 1, and then minus 1, and then plus 2. It's a lot going on there. Okay, so I'm plugging in the x value negative 1 in for x here and finding what the y value equals using my calculator. So that gave me negative 6. Okay, next up, I want to go ahead and plug in x is 0. So I could try to highlight back over this same equation and delete a couple things here because all I need to do is plug in multiply by 0. And then minus 1. Okay, so negative 2, just making sure I plug that in right. Okay, perfect. So that gave me 0. And then using the same one, I'll highlight over it again, and then go back to the 0, change it to plugging in now a 1. We get 3 over 2, which is 1.5. And then plugging in 2, highlight over the same one again, change it to a 2. All right, we get 15 over 8. I'll use the 2 arrows to get the decimal version of that. So that's 1.875. And then lastly, highlight over the same equation again, and then change the 2 to a 3. We get 63 over 32, which as a decimal would be 1.6875. 1.9687. All right, for the graph, I can just go ahead and plot those points. So negative 1 and negative 6, 0, 0, 1 and 1.5, 2 and 1.8, which is 1 point. It's like really close to 2, but not exactly 2 yet. And then 3 and even closer to 2, but not exactly 2 yet. So you can see that we're going to continue to get like really, really close to 2, but it's never going to touch 2 or pass 2. So our horizontal asymptote is at y equals 2. I could also have determined that based on the fact that we are shifted up 2 units. So if you're shifting up or down, that's where your horizontal asymptote is moving. So the graph, let me pick a darker line here. Graph looks something like this. Okay, with that horizontal asymptote, again, at y equals 2. All right, now that I have my graph, I can go ahead and determine all of these key features by just looking at the graph. That's why making a sketch is really important whenever you're asked for key features. Even if they don't ask you to graph, whenever they're asking you for key features, you want to make at least a rough sketch. So for the domain, for all exponential is all real numbers, negative infinity to positive infinity. The range will depend on where the horizontal asymptote is and if the graph is above that horizontal asymptote or below it. So in this case, it is below it. So that means that I will have all negative y values, and then those y values will go up to the 2, where the horizontal asymptote is, but never actually touch 2, never actually get to the 2 or pass it. So my asymptote is at y equals 2, where all of the y values end up stopping. Then for the increasing interval, that would be the entire graph, since notice we did start with a growth, but that was reflected over the x-axis. So just like you see here, it ends up, flipping over. Actually, it was the decay because of the, it's also reflected over the y-axis. So there was a double reflection here. But either way, as you see visually on the graph, if we follow it, it is going up. Decreasing would be none. My y-intercept is at 0, and that's actually also where my x-intercept is at. Both, the graph touches the line at the origin, which means that both the x and the y-intercept are at 0. Okay, number 15. So you deposit $5,000 into an account that earns 3% annual interest. Find each of the following balances after 10 years if the interest is compounded with the different frequencies. Okay, so whenever we are compounding continuously, the formula that we're going to use is A equals P times e to the power of RT. If we're compounding a certain amount of times, we're going to be using the formula A equals P times 1 plus R over N to the power of NT. So this formula applies not only for part A, but also for part B. Anytime that you are compounding a certain number of times, this is the formula that you use. Now, for both of these, the time is 10, or for all three of these, I should say, the time is 10 years. And for all three of them, the rate is the 3% as a decimal, so 0.03. Okay, so T is 10, and R is 0.03 for all of them, and also P, because you start depositing $5,000. That is the same on all of them. So P is 5,000 on all three. Now, where the difference comes is in N. On part A, N is semi-annual, which means 2 times a year. So on part A, N is 2, whereas on part B, it is compounded daily, and there's 365 days in the year. So on part B, N is 365. And that's all the information that we need. So let's go ahead and complete part A first. So on part A, my amount that I have at the end of 10 years is going to be the 5,000 that I put in times 1 plus 0.03 divided by 2 to the power of 2 times 10. So if I simplify in here, which I could use my calculator, 1 plus 0.03 over 2, and notice it's 1 plus the 0.03 is being divided by 2, the 1 is not being divided by 2. So that's 1.015. So it'd be 5,000 times 1.015 to the power of 20. So I can use my calculator and plug that in. So 5,000 times 1.015 to the power of 20. And we get 6,034 and 28. You could also say 27 because they don't really have that full next cent, but either one is fine. Okay, so I'm just going to go ahead and round it. 6,734 and 28. All right, what about for the compounding daily? So if we keep the same information, but we compound it daily instead. So that would completely change the number here, because even though 5,000 remains the same and the 1 plus and the rate 0.03 remains the same, we're going to be dividing 0.03 by 365. And then in the power, it won't be 2 times 10, it'll be 365 times 10, since n is 365. So I could use my calculator again to simplify the parentheses, which I could actually just highlight back over this original one and then change the denominator from 2 to 365. So that's 4 zeros. So, and this is a guesstimate because obviously I have to cut off the number at some point. I only have so much space on this here, so I'm gonna write it as 1.0008. And then 365 times 10 would be 3,650. To get the most accurate read of the number, I'm actually going to use the ANS feature on my calculator. So it'll be 5,000 times, and then what I got as an answer, which will copy the previous answer that I got, which would be the 1.00829192. I could have also typed it out. And then to the power of 3650. Okay, so that was 6,749 and 21 cents. So notice that we actually get some more money when we compound more frequently. Okay. Keeping the same amount of money in the same kind of account with the same rate, and just changing how much we're compounding. So by this, it would make sense that the continuously should be a little bit more, right? So, but notice for the continuous, we use a completely different formula. We're going to do the principal 5,000, and that's multiplied by Euler's number to the power of the rate times t, which is 10. So I'm going to go ahead and plug that into my calculator. 5,000 times Euler's number to the power of the rate multiplied by time t, 10. So we get 6,749 and 29 cents. So we did actually get some more money with compounding continuously. 8 cents. All right. So savings account earns compound interest at a yearly interest rate R. The following gives the current amount in the savings account after T years. Okay, what is R as a percent? Okay, so they're asking us for the rate as a percent. Notice here that N is 12. Okay, and remember that this in here, the formula is 1 plus the rate over N. So this 1 is a part of the 1 here. And so that tells us that the rate divided by N, which is 12, is the 234. So this was the regular rate, yearly rate, divided by 12. So if I multiply by 12, that gives me back the rate yearly. So the yearly rate divided by 12, since N is 12, was the 0.234. So if I multiply 12 back in, then I will get the yearly rate, which is 2.808. They want me to write it as a percent for the answer, so I will move the decimal point twice to the right. So that's 280.8%. Okay, and then last, they want us to rewrite the model to illustrate what the current amount of money would be if the interest were compounded quarterly. So now they just want us to change N and use N as 4. So I will keep the same kind of situation AT equals 1400. But then in here, rather than doing 1 plus the rate, which is 2.808, and then dividing it by 12, which would give me back to the 0.234, I'm going to divide it by 4, since quarterly means 4 times a year. And then the power, instead of 12t, that'll be 4 times t. So of course, last thing I need to do is simplify inside of here. So I can use my calculator to do 1 plus 2.808 over 4, which is 1.702. So quarterly, this should be A of t equals 1400 times 1.702 to the power of 4t. Okie dokie. Number 17, they want us to go ahead and rewrite the equation in exponential form. All right, so that's the little song and dance. We're going to go ahead and the base of the log becomes the base of the exponent, and then the log number and the result switch. So z goes to the power, y goes to the other side. Next, 14 to the power 2 equals 196, which we can also confirm, because 14 squared is 196. And then ln, remember, is log with the base e. So if I write it that way, I can clearly tell that the base is e, so the base of the log becomes the base of my exponent, and then I switch the other two, so power 1.386 equals 4. Right, on 18, we're going the other way. So now we're going to write the equation in log form. So I'm going to take the base of the exponent, that becomes the base of the log, and I switch the exponent result and the exponent power. So 324 equals 2. On part B, notice that there is no exponent here for 49, but I know that at 49, if that's the square root, then the power for 49 is a half. So this would be log base 49, 7 equals 1/2. Okay, for part C, that would be log base 3, 1 over 81 equals -4. Okay, for number 19, notice it says that you do not need a calculator for these. We are actually going to use the identity that if you have the log base b, that just equals 1. So basically, if the log number and the log base is the same, they basically cancel out, and you just get, like, if I had a 2 in front, then it would have actually equaled 2. So log base bb is itself is 1. So if it's multiplying by anything or something like that, then it kind of, like, you can imagine the log base bb will cancel out. So if we move this 27 is actually 3 to the power of 3. So if I change this to log base 3 to the power of 3, 3 times 3 is 9, times 3 is 27. Yeah. So this is 3 to the power of 3 to the power of 2, since 27 was already squared. So this is really log base 3 to the power of 6. And remember, the rule for the power rule for logs says that the 6 with the power, I can instead write it as multiplying out in front. So this is 6 times log base 3. And the log base 3, the log base and the log number is the same, so that cancels out. So this is really just 6 times 1, which is 6. Okay, for part B, notice that this is, again, e to the power of 7, and ln is log base e. So this is 4 times log base e to the power of 7. That power 7 I can bring out in front. So now 4, which was already in front, stays. Then another 7, because of the power 7, I'm using the power rule there. And then the log base e stays. Log base e would cancel, so this is just 4 times 7, which is 28. Next, part C, we have log, and there's no base here. Remember, no base means the common log, which is base 10. So log base 10, and then notice that I have 100,000, which is 1, 2, 3, 4, 5 zeros behind, the 1. So that is 10 to the power of 5. 10 times 10 times 10 times 10 times 10 is 100,000. You can confirm that on your calculator. So using the same power rule, this would be 5 times log base 10, 10. The log base 10, 10 cancels, and so we just get 5. Okay, next they want us to go ahead and expand the log. So that means that we're going to take everything that is already condensed and together, and we're going to write it out. So the first thing I'm going to do here is use the product rule, because these two are multiplying. X to the power of 2 and the square root of 22 are multiplying. So I'm going to expand that by using the product rule, which says I'm going to add these logs. So log base 3 x squared plus log base 3 square root of 22, which 22 then has a power 1/2 because it's the square root. So the index is 2. Next, I'm going to use the power rule and bring that power and expand that out in front. So my final answer is 2 times log base 3x plus 1/2 log base 3, 22. And I could write it as 1/2 times log base 3, 22, or I could have written the log base 3, 22 divided by 2. It's, of course, the same. Okay, next up, part B. So notice that here I have this 5 that is on both. So the first thing I'm going to do here is I'm just going to simplify this in here a little bit before I go into any expanding, because I want it to be a little bit easier. So I'm keeping my log number right now. I'm not really expanding. I'm just simplifying and distributing the power 5 to the x and the power 5 to the y 4. So this would be y to the power 4 to the power 5. So it would be y to the power 20. Now I'm going to go ahead and apply the quotient rule and expand this out. So the quotient rule says I subtract the log. So I would be log base 8 x power 5 minus log base 8 y power 20. And then the last step would be to apply the power rule, bring that power out in front. So my final answer here would be 5 times log base 8x minus 20 times log base 8y. Okie dokie, moving on to part C. On part C, oh, little snooze there. On part C, we have, again, I have a power of a power here. So I'm just going to, before I go into expanding, I'm just going to go ahead and simplify that log. So I just have, the log simplified as best as I can. So I'm going to distribute the power 3 to both of these in here. So that would be u to the power 9, v to the power 3. Now that I simplified that, I'm going to go ahead and apply the product rule. So the product rule says that I add u log base 9 u to the power 9 plus log base 9 v to the power 3. And then now apply the power rule, multiply out in front 9 times log base 9u plus 3 times log base 9v. All right, last question. This is ln, and there's nothing else to simplify in here, so I'm going to go ahead and start by applying the quotient rule, so I could get rid of the fraction. So I would expand that out. It would be ln of the numerator, AB, minus ln of the denominator, which is c to the power 6. Now, normally, we would you do the power rule, right? So the second part is going to be 6 ln c. That part should be very obvious. But also, notice that the numerator AB was multiplying. So I have to expand that out. So my final answer would be ln A plus ln B minus 6 ln C. Okie dokie. All right, moving on to number 21. They want us to now do the reverse. Now it is expanded. We're going to go ahead and condense it together. So I'm going to do everything in reverse, right? So the last thing I did on the expanding was apply the power rule. The first thing I'm going to need to do here is apply the power rule. So I'm going to bring all numbers that are multiplying in front up to the power. So this would be log base 8a to the power 15, and then plus, there's no number there, so the log base 8b will stay by itself. Now I'm going to apply the product rule. If I'm adding, that means that I'm going to multiply those two log numbers together. So my final condense will be log base 8, and then one log number altogether, it will be a power 15 multiplied by b. Okay, part B. So now we have 4 and 2 that are multiplying in front. So I'm going to do the power rule. So this would be ln u power 4 minus ln v power 2. And then I'm going to apply the quotient rule. So if I'm subtracting, that would be ln u to the power 4 in the numerator divided by v to the power 2 in the denominator. And that is my final answer for part B. All right, and the last one, part C, I'm going to multiply that 5 power rule in front, and this is 1/2 that's multiplying. I'm going to apply that power rule as well. So this is log C power 5 plus log A power 1/2. Next, apply the product rule. So plus means that it is a product. So I'm going to do a log, and then C to the power 5 multiplied by, and then a to the power 1/2 is the square root of a. Okay, you can put the parentheses around the log number, or leave them off. If you don't put it, it's assumed that the first term is what the log number is for. Okay, so next up, I'm going to go ahead and do number 22. So solve, and then they're asking us to round to the nearest thousands if I need to round at all. Okay, so in order to solve this, I need to condense these logs together. Notice that on the left side there I have 2 logs out, so I need to go ahead and condense that together. So I'm going to bring the 3 up, so this would be log base 5 x power 3, and then minus log base 5 1/2. This plus 2, I could actually subtract 2 so that I could bring it over to the other side, because the right side has a number by itself. 2 is a number by itself, so I want to bring that over with the other number by itself. And that'll simplify the left side a little bit there. Okay, because the plus 2 is not for the log number. The log base 5 is for the 1/2. So now I can condense this further by doing the quotient rule. So this would be log base 5, and I'm doing x power 3 divided by 1/2. So I'll write it down first, and then I'll show you what that would look like. Because obviously this is like a fraction within a fraction, which is pretty confusing. So if you're dividing 1/2, that's the same thing as multiplying the reciprocal 2. So it's really log base 5 2 times x cubed. So it's not that I'm applying the product rule, I am applying the quotient rule, it's just that I'm dividing a 1/2, which is multiplying the reciprocal of 1/2, which is 2. So mathematically, these two are the same. So now I have log base 5 some number equals 4. So now, since my variable is in the log, I'm going to go ahead and switch this to exponential form. So that would be 5 power 4 equals 2x cubed. Okay, so all I did there was switch it to exponential form. So now that I have it in exponential form, I can simplify. 5 to the power of 4 using my calculator is 625. Then to get x by itself, I could divide by 2. So now I have 625 over 2 equals x cubed. And then cube root both sides. Now, they did tell me to round to the nearest thousands, so I could go ahead and just punch this into my calculator and then round it. So on my calculator, I could do the cube root of 625 over 2, which is 6.786. So roughly, approximately 6.786. Okay, let's go ahead and do part B. Now, part B, we have log base 2 some number equal log base 2 some number. So if I'm doing the log base 2 and that equals another log base 2, then the two numbers here must be equal to each other, right? So that tells me that negative 5x minus 2 has to equal 2 minus 4x. So to solve, I can go ahead and add 5x on both sides and subtract 2. Negative 2 minus 2 is negative 4. Negative 4 plus 5 is 1x. So x equals 4. Negative 4. Okay, for part C, we have log base 12 some number equal log base 12 some number. So that means, right, that the 4x plus 10 must equal 2x plus 4. Okay, because the two log numbers will cancel. So subtract 2x. And subtract 10. We get that 2x has to equal negative 6. And when we divide by 2, we get x equals negative 3. Now, here's the catch on this one. When you're plugging in negative 3 in here, you would get negative 12 plus 10, which is gonna be a negative number. And remember, when you're taking the log of any number, that number has to be positive. Okay, so actually, this answer will give us no solution. If you checked it by plugging it back in, you would see that when I did the log, let me try to do the log of 4 times negative 3 plus 10. To check it, I get domain error. Okay, you cannot take the log of a negative number. So that one gives you no solution. If I go back to the previous one on part B, we got x is negative 4. But plugging in x is negative 4 would make this positive and would also make this positive since we're multiplying x by a negative. So it's not a problem on that particular example since we're not taking the log of a negative. So just be careful circling your final answer and make sure that you're not taking the log of a negative number. Okay, next is part D. So first I want to get the exponent by itself. So I'm going to divide by 4. So now I have e to the power of 2.7x equals 33 over 4. And I have an exponential equation with a variable in my exponent. So I'm going to switch this to log form. So it will be log base e, 33 over 4 equals 2.7x. Log base e is ln, and to get x completely by itself, I would need to divide by 2.7 on both sides. So in my calculator, I will find what ln 33 over 4 is, and then take that number and divide it by 2.7, and that'll be what x equals. Now they asked us, remember, to round to the nearest thousands. So let's use our calculator. ln 33 over 4, and then take that number and divide it by 2.7. So we get 0.782. So x is roughly about 0.782. Okay, and moving on to part E. So on part E, we have another exponential equation here. So I'm going to first get the exponent by itself. So I'm going to divide by -16 on both sides. So that would be 10 to the power of 6x equals, well, -80 divided by -16 will be a +5. And then now I have a log, or I need to change it to a log form. So I'm going to do log base 10, 5 equals 6x. And remember, base 10 is the common log. So I could just type into my calculator log 5, and then take that and divide it by 6, and I will get x completely by itself. So x will equal whatever log 5 is divided by 6 on my calculator. So again, I'll take out my calculator. I'll do log 5, and then that number divided by 6. So it'll be 0.116, roughly. All right, last one, part F. So I want to get the exponent by itself. So I first have to add 2. So now I have 9 to the power of x divided by 4 equals 7. And then still the exponent is not by itself. So next I will need to multiply by 4. So now I have 9 to the power of x. So now I have the exponent by itself. And then 7 times 4 is 28. Okay, so now I have my exponent by itself, so now I'll switch it to log form. So I have now log base 9, 28 equals x. Now on my calculator, log is common log base 10. So in order to punch this into my calculator, I will need to do the change of base formula. So I will do log 28 divided by log 9. So on my calculator, log 28, and then divided by log 9, and that gives me 1.517. So x is roughly that number. Okay. That is it for the review. So I hope it was helpful, and good luck on the test, guys.